Hey there, science fans! Have you ever stopped to think about light? It's everywhere, and it's amazing. Light allows us to see the world around us, from the vibrant colors of a rainbow to the intricate details of a flower. But light is more than just what we see. It's a form of energy that travels at an incredible speed, about 186,000 miles per second. That's like going around the Earth 7 times in just 1 second. Light is made up of tiny particles called photons. Think of photons as little bundles of energy that are constantly moving. These photons travel in waves, similar to the waves you see in the ocean. Light is essential for life itself. Plants use light to make food through photosynthesis, providing us with oxygen and energy. We use light in countless ways, from lighting our homes to transmitting information through fiber optic cables. So, let's dive in and explore some of the fascinating ways light interacts with the world. Have you ever looked in a mirror and wondered how it works? That's the magic of reflection. Reflection is the bouncing back of light when it hits a surface. Think about a tennis ball hitting a wall. The ball bounces back at an angle. Light works in a similar way. When light hits a smooth surface like a mirror, it bounces back at the same angle it hit the surface. This is why you see your reflection in a mirror. Reflection is happening all around us. We see objects because they reflect light into our eyes. Shiny surfaces like spoons, metal and water can all act like mirrors, reflecting light and creating reflections. Even objects that don't seem shiny reflect some light. This is how we are able to see them. The next time you're outside, take a look around and notice all the different ways light is being reflected. Have you ever noticed that a straw in a glass of water looks broken at the surface? That's because of refraction. Refraction is the bending of light as it passes from one medium to another, like from air to water. Imagine you're driving a car from a smooth road onto a bumpy dirt road. The car will slow down and change direction because of the rough terrain. Light behaves in a similar way. Light travels at different speeds in different materials. When light passes from air to water, it slows down and bends. This bending of light is what causes the straw to appear broken. Refraction is what allows us to see through lenses, like those found in eyeglasses, cameras, and telescopes. Lenses are specially shaped pieces of glass or plastic that bend light in specific ways, allowing us to see images more clearly. Here's a mind-blowing fact. Light can bend around corners. This phenomenon is called diffraction, and it happens when light waves encounter an obstacle or a narrow opening. Imagine ocean waves approaching a narrow opening in a harbor wall. The waves will spread out after they pass through the opening. Light waves behave similarly. When light passes through a small slit or around an obstacle, it spreads out and creates a pattern of bright and dark areas. This pattern is called a diffraction pattern. You can see diffraction in action by looking at a CD or DVD. The closely spaced tracks on the disc act like a diffraction grating, creating the rainbow of colors you see. Diffraction is also what causes the fuzzy edges of shadows. Section 5. Reflection, Refraction, and Diffraction, a colorful trio. Reflection, refraction, and diffraction might seem like separate phenomena, but they often work together to create the visual world we see. One stunning example is the rainbow. Rainbows are formed when sunlight is refracted, reflected, and dispersed by water droplets in the air. Sunlight enters a raindrop and is refracted, bending as it slows down. The light then reflects off the inside surface of the raindrop. As the light exits the raindrop, it is refracted again. During this second refraction, different colors of light are bent at slightly different angles, separating the white sunlight into its component colors, creating the beautiful arc of a rainbow. The interplay of reflection, refraction, and diffraction is essential for many natural phenomena and technological advancements. These phenomena are not just cool science concepts, they have real-world applications that impact our lives in countless ways. Section 6. Light in Action, Technology at Play. The principles of reflection, refraction, and diffraction are at the heart of many technologies we use every day. From eyeglasses to telescopes, these phenomena have revolutionized the way we see and interact with the world. Eyeglasses and contact lenses use refraction to correct vision problems. Lenses are carefully crafted to bend light in a way that compensates for the eye's inability to focus light properly on the retina. Cameras and telescopes rely on lenses and mirrors to capture and magnify distant objects. Lenses in cameras focus light onto a sensor, creating an image. Telescopes use lenses and mirrors to gather and focus light from distant stars and galaxies, allowing us to explore the vastness of space. Fiber optic cables, the backbone of modern communication, use total internal reflection to transmit information as light pulses. Light is confined within the fiber optic cable, bouncing off the walls and traveling long distances with minimal loss of signal. Section 7. Exploring the microscopic world. Diffraction to the rescue. Diffraction, the bending of light around obstacles, plays a crucial role in microscopy, allowing us to see objects too small for the naked eye. Optical microscopes use lenses to magnify tiny objects, but diffraction limits the level of detail that can be resolved. Electron microscopes overcome this limitation by using a beam of electrons instead of light. Electrons have a much shorter wavelength than visible light, allowing for much higher resolution. Diffraction patterns created by the interaction of electrons with the sample provide valuable information about the structure and composition of materials. X-ray crystallography, a powerful technique used to determine the three-dimensional structure of molecules, also relies on diffraction. By analyzing the diffraction patterns produced when X-rays pass through a crystal, scientists can determine the arrangement of atoms within the crystal lattice. Section 8. Beyond the visible light's extended family. Visible light, the rainbow of colors we see, is just a small part of the electromagnetic spectrum. The electromagnetic spectrum encompasses a vast range of electromagnetic radiation, from radio waves with wavelengths longer than a football field to gamma rays with wavelengths smaller than an atom. Radio waves are used for communication, broadcasting, and radar systems. Microwaves are used in microwave ovens and for communication with satellites. Infrared radiation is used in thermal imaging and remote controls. Ultraviolet radiation is responsible for sunburns and is used in tanning beds and sterilization processes. X-rays are used in medical imaging and security scanners. Gamma rays, the most energetic form of electromagnetic radiation, are used in cancer treatment and to study the universe. Section 9. Keep exploring the wonders of light. Light is an endlessly fascinating subject, and there's always more to learn. From the way it interacts with matter to its role in technology and the universe, light continues to amaze and inspire us. So keep your curiosity shining bright and never stop exploring the wonders of light.